Section 4.2 is on irrational numbers. So the set of numbers which we use in everyday life is known as real numbers, and that's denoted by the symbol. It's like an uppercase R, and sometimes it has a double line. If you have like a regular R, and sometimes it's written with like a double line there, it kind of looks like that. But anyway, there are two types of numbers that real numbers are broken up into, and that's the rational and irrational numbers. Rational numbers are denoted by Q, the symbol Q, and are numbers which can be written in the form of a fraction a over b, where a and b are integers, and b cannot be 0, because if b is 0, then it would be an undefined number. So the rational numbers would include your sets of natural numbers, which are denoted by n, and they would be what we call our natural counting numbers, like 1, 2, 3, 4, 5. Our whole numbers, which are the natural numbers along with 0, and whole number symbol, it would be a W. Integers, symbol would be I, and integers include all your whole numbers plus all the negatives of the natural numbers. So 0, 1, 2, 3, 4, and so on, and -1, -2, -3, and so on in the negative direction. And also included within the rational numbers are decimal numbers which can terminate, for example, like 0.5, because that's 5 over 10 or a half, and decimals that have a repeating pattern. For example, 0.3333 can be written as 1/3. Irrational numbers would be the other set of numbers that our real numbers are made up of, and irrational numbers have a symbol of Q with a line over the top of the Q. This line just got shifted a little bit, it should be over the top of the Q. And they're numbers which cannot be written in the form of a fraction or quotient of two integers. And because they're not rational, their decimal form would not repeat and would not terminate. So they wouldn't have any repeating patterns, and they would not terminate. So the irrational numbers would include radicals that do not simplify to nice numbers, like √2, the cube root of 5, and so on. Something like square root of 4 would not be irrational, because the square root of 4 can be simplified to 2, which is a rational number. Decimal numbers that do not repeat and do not terminate. For example, 3.1211121121112 ... so on. There's no repeating pattern there, and it just keeps going. So that would be an irrational number. There are also some special numbers like pi and e, which are also non-repeating, non-terminating decimals. So they would be included in the set of irrational numbers. Okay, so now we're going to try to create a diagram which shows the relationship between these sets of numbers that make up the set of real numbers. So the first thing I have to do is correct an error here. This little line right here is not supposed to be over the R, it's supposed to be over the Q. So can't really erase it. So I'll just draw it over the Q and just pretend that it's not there. Okay, so the first thing we have to do is figure out where each of those symbols go to represent the number systems as they fit together. So basically the whole set of numbers is made up of rationals and irrationals. So that would be your set, that box basically would be the set of real numbers. And then you have your irrational numbers would be this smaller circle here kind of off by itself with the Q with a line over it. And even though the set of rational numbers and the set of irrational numbers are considered an infinite set, like there's more every time, you can always come up with more examples. Basically there's no end to them. There's not a finite set of numbers in the rational or irrational set, but when we think about it, there seems to be a lot more rational numbers for every irrational number that we have. So that's why we kind of consider the irrational numbers to be a smaller set of numbers. All right, so the next circles that are basically embedded within each other, they would all be representing rational numbers, which can be broken down into subsets of natural numbers and whole numbers and integers. So because the rationals is the biggest group here, the rationals would be the outside circle, and that would contain the integers and the whole numbers and the natural numbers. The smallest of these sets would be the natural, because that does not include 0. And then the whole numbers would include all the naturals plus 0, so that would be the next set. So it would be all those plus, basically the natural numbers plus 0. And then the integers would include your whole numbers and natural numbers, but also some other, the negatives of the natural numbers. So that would be outside. And then of course Q contains all of those sets. Then it says to place the following numbers in the correct region. So 1 would be a natural number and a whole number and an integer and a rational and a real. So if we put it in here, then it would belong to all of those sets. And -5 is not a natural, is not a whole, but it is an integer, and it is a rational and a real. So putting it in here, we know that it's a set of the outside circle and the outside box. 8.2 is a terminating decimal, so that is a rational number, but it's not an integer, whole, or natural, so it would be out in this part of the circle. Root 7 is, if you look at its decimal form, is non-repeating, non-terminating, so that would be out here in the irrational numbers. 0 would not be a natural number, but it would be a whole, and therefore an integer, and therefore a rational, and therefore a real. The cube root of 8 is the same thing as 2. So that would be a natural, and necessarily a whole, an integer, a rational, and a real. And so 2/3 would be a rational number, but it would not be an integer, a whole, or natural, so it would be out here, because that is the definition of rational number. It means it can be put in the form of a over b, where a and b are integers, so basically form of a fraction, so that means it would be rational. And 12/3 is in the form of a fraction, but it reduces to 4, so therefore we would have that in with the natural numbers, because it's natural, whole, integer, rational, and then real. Okay, so the next exercise asks us to basically identify whether they're rational or irrational and your reasons. So anything that can be written in the form of a fraction where the numerator and denominator are integers would be rational. So the first one would be rational. And we'll just say form a over b. And root 14, if you look at that or think about that, the root of 14 is not a nice number. So that would, its decimal, if you looked at it in terms of a calculator, would be non-repeating, non-terminating. It uses up every space on the calculator, and you can assume for the most part that any radical that doesn't work out nice will be irrational. So that would be irrational. And we'll just say non-repeating, non-terminating decimal. Cube root of 8/27 is the cube root of 8, which is 2, over the cube root of 27, which is 3. So that would be a rational number. And again, it's the form of a rational number, a over b, where a and b are integers. And this square root of 49/16 would be the square root of 49, which is 7, over the square root of 16, which would be 4. And again, that would be a rational number, because it has the form of a over b, where a and b are integers. The cube root of -30 is not a nice decimal representation when you check that on your calculator, or just think about it in terms of estimating. So therefore it would be irrational. So non-repeating, non-terminating. Decimal. And 1.21 is rational, because it is a terminating decimal. And the cube root of 64 is 4. Oh, sorry, didn't mean to write that there. So it's 4. So that would be rational, because it can be written in a over b form, and it's an integer. 0.3433343334, that is not a repeating pattern. It's a non-repeating, non-terminating. decimal. The next one is 0.34. You look at it, the 3-4 is repeating, so that's a repeating pattern, so we'd say that that would be rational. So we call that a repeating decimal. And the last one, 7, would be rational because it is an integer, which is a rational number. And integers can be written in the form of a over b by putting them over 1. So that would be a rational number. All right, so now if we're going to use a number line to order these numbers from least to greatest, you might want to look at the decimal representation, and we're just going to use our calculator rather than approximation here now, but root 2 is around, the square root of 2, sorry, is around 1.4 approximately. Whoops. And then this cube root of -5 will be around -1.7. These are all approximations. And the cube root of 7 will be around 1.9. And the square root of 12, use our calculator, is around 3.46, so around 3.5. And the fourth root of 32 is around 2.4. So if we look at those values, the square root of 2 is around 1.4, so this looks like that would be the square root of 2. And then the cube root of 7 would be this one. Skipped over the cube root of -5, which is the only negative value that we have here, so that would have to be this one here, which looks about right on the number line, and -1.7. And then we have the square root of 12, which is 3.5, which would be right here. And then 2.4 is around the fourth root of 32. Okay, in this next exercise, you're asked to indicate to which number sets each value belongs. So the first one simplifies to -4. The cube root of -64 is -4. So it's not a natural number because it's negative. Same thing, it's not a whole number, it's a negative value. But it is an integer, and it is a rational number, and it will be a real number. The square root of 100 is 10. So that is a natural number, a whole number, an integer, a rational, and a real. 2.08 is a terminating decimal, so it's not natural, whole, or integer, but it is rational because it terminates as a decimal, and therefore it is also real. 0 is not natural, but 0 is included in the set of whole numbers, integers, and necessarily rationals and reals. The next one, you have 5, 7, 1, 2, 7, 1, 1, 2, 7, 1, 1, 1, 2. So it doesn't seem that it's a repeating pattern. So that would be considered irrational because it's non-repeating, non-terminating. And it would also still be a real number. The next one is the cube root of 64, which is 4, over the cube root of 8, which is 2. And that reduces to 2. Or you could have done 64 over 8 is 8 and cube root of 8 is 2 as well. You could have done it that way as well. But that is a natural number, is a whole number, is an integer, and is a rational and therefore real. A half is not a natural, whole, or integer, but it is rational because it is in the form of a fraction where the numerator and denominator are integers, and it is therefore a real number. The cube root of -1 is -1, so that is not natural or whole because it's a negative, but it is an integer and it is a rational number and it is a real number. The next one has 0.8315, 315, 315. So that's a decimal that doesn't stop, but it is has a repeating pattern. So that would be a rational number. and it would necessarily then be real as well. And the last one, the square root of 81 is 9, over the square root of 25 is 5, so that would be not a whole number, natural or integer, but a rational and real. Next question asks you to determine whether each statement is true or false. So, first one, basically it says that all natural numbers are also integers. Well, that will be true because the natural numbers are a subset of the set of integers. So every natural number is also an integer. The set of integers, next one, the set of integers is nested within the set of rational numbers, and that's true. The set of rational numbers is larger than the set of irrational numbers. And technically, we talked about that earlier. They're both infinite sets, but it seems like there's a lot more rational numbers for every irrational number, so I would say true to that. All integers are rational numbers, and that would be true, because the integers are a subset of the rational number set. They're embedded within the rational numbers. The set of real numbers consists entirely of rational and irrational numbers. That's also true. The set of real numbers is nested within the set of naturals, and that's false, because if that were the case, then all real numbers would also be natural. That's not true. All natural numbers are real. Had the R and the N been switched, then it would be true, but the way it's written there, it's false. All irrational numbers are real. That is true. The set of whole numbers contains 2 extra numbers not in the set of natural numbers, and that's false. The only number that's in whole numbers but not in natural is 0. All whole numbers are also natural numbers. No, that's false as well, because 0 is not natural. Now, had they turned that statement around, all natural numbers are whole, that would be true. The square root of all numbers is in the set of irrational numbers, and that is false, because if you can come up with one example for which the statement is not true, then it's considered a false statement. So our counterexample, that's called, would be the square root of 4 is 2, and 2 is rational. So at the bottom here we have some questions from pages 211 and 212 that you can try to practice the material you've learned in this section there in your textbook.